all the way from Norway, Bergen. He's representing Heriot-Watt University to give a talk.
Okay, thank you. My name is Arne Skauge, and I'm starting a new period as chair from Heriot-Watt University. I earlier has been with the University of Bergen in my hometown, Norway, but have now changed. So I'm very much appreciated that to start up at Heriot-Watt. So, yeah, the presentation is called Maximizing Oil Recovery Under Energy Transition. It's the chair program is also coupled to EOR, so it's low net carbon EOR and energy transition. So thereby we are coupling the oil production, but also looking at the CO2 footprint we are making with the oil production and trying to minimizing the energy we are spending on the processes. So this is a slide which is very busy, but it's I just want to highlight some minor things that on the bag processes we've been working quite a lot. We are continuing on that in new direction. You will see some results on that. Then we've gone back to more fundamental studies, looking at modeling unstable processes, which is very difficult. Many has tried, but there hasn't been much success. So we came up with a kind of a procedure in order to at least get good results on the early stage of these processes. Everything on these processes needs upscaling, and upscaling is part of this this project. It's a JRP project also, which is supported by the industry. Another factor that has come in is all the way to your right. Is looking at energy efficient polymer flooding. And why is that a key issue? Well, when at late stage of your water flood, you're coming up with a very high water cut, and the polymer is there to accelerate oil production, reduce water cut, and reduce greenhouse gas emission for the production period. So on the late stage of production, this could be a goal. This procedure of modeling viscous fingering is something that we have developed over time, and I will show you some demonstration of how it has been applied later on. But it's a four-step type of process in the way of first, define grid size, and that is to choose sufficient fine spatial grid for numerical simulation. And you see that on your right hand side, we are looking at the dispersivity gain length scale. So at any length scale is characterized with a dispersivity, and the example here is shown by 1 foot model. Then the calculated dispersivity from this type of correlation would give us 0.05 centimeter. And the block length should be 2 times the dispersivity, and it comes to 0.1 centimeter or 1 millimeter. So if I want to model this with a viscous unstable process by, for instance, on a 2D, by 30 centimeter, I will have 300 by 300 blocks. in order to describe this system in a good way. Another kind of precondition we need for viscous instability is that we need a random correlated permeability field. And then it's, this is not so complicated as it looks. And you could a priori kind of generate a random correlated permeability field. The purpose is that you have at least 2 orders of variations in permeability. And the randomness is initiating fingers. That's is the purpose. Then we are trying then to put the right velocity into the fingers which are moving ahead. And that has been done by doing one-dimensional fractional flow approach and looking at the shock front saturation. So we want to have as high water saturation into the fingers as possible. And we are maximizing the total mobility. And that is the same as defining a least resistant pathway through the system. So by this approach, we are then able then to, in a simple way, it's non-unique, but it's you have a pretty good recipe in order to get a viscous fingering in a good, reasonable way. So I will show you some examples of that. First, so over this year, we have published 3 papers, one on water fingers, one on polymer flood at adverse mobility ratio, and one on fluid flow, and especially in gas injection and WAG. So on the first case, I'm trying to do this rather quick. And the first paper here is then referring to water fingers. And what we see here on the grayscale here on the top left is that we see experiments where water fingers is, we have water injection on the bottom, and we see fingers growing up. It's more fractal in the beginning, and then it's somewhat collapsed in front. But that comes at the very late stage, especially after the breakthrough. So in this case, we had a breakthrough of 0.04 volumes. And the contrast in this case was an oil of 2000 centipoise, and we injecting water with 1 centipoise. Then we're trying to match this. We're able to match production and pressure in several ways. But the uniqueness is that by this approach, then we're able also to catch the fingers being formed. So the procedure we have developed has been successful in the sense of not creating identical pictures, because this is not a history match. It's just a priori kind of a prediction of what's happening. And we see by this approach and maximizing the mobility, then we are able then to get the breakthrough at about the right time. The number of fingers seems reasonable. And up to the breakthrough, we have a very good match in all purpose. The problem is on the later stage, then we see that the fingers are spreading into channels, and it's spreading too much in that sense. But that's another issue. So on the early stage, we have a very good match, we think. And we started out also with the matching experiment of polymer flooding, which is number 2 there. That's a tertiary polymer injection. And what the pictures are showing all the way to your right is showing a change after water flood. So the red color is the increased oil saturation. Blue color is the increased water saturation. So by injecting polymer, we see that we are crossing oil into the water channels already being made. So we have a cross flow into the channels, and that's the least resistant pathway. It would rather displace water at 1 centipoise than moving forward the oil at 2000 centipoise over the whole length. So, and this process is going on, and what looks like the instability on the water is not an instability. It's a kind of a piston-like frontal movement, because what the black areas in between there is area which has already been swept by the water. So now you get a uniform front moving upwards with banking oil on top of it. And we are seeing that in the simulation, we are able then to get the banking right, we get the total production right, we get the pressure fairly well. And we are quite satisfied with it on different cases that we are able then to having the oil bank formation moved. And the light color you see on the simulation cases is actually the polymer front moving upwards. So then we are moving over to application to viscous fingering in gas injection and bag analysis. We have a poster on that, so we can go much more in detail than I can do in this presentation. But this is just one example. And you're getting it before it's going to be presented. It's going to be presented at ADIPEC in 3rd of November. So you are the first to see it before it's out in the open. But in this case, it's I'm only showing that I'm using the max mobility type of approach for gas, and trying then to maximizing the gas mobility and the fraction of flow to get the highest gas saturation in the finger front. And by that approach, I'm getting this kind of behavior. And this is a 500 meter from injector to producer, 50 meter thick cross section. And what we see here is then on top is the water saturation, the gas saturation after 0.2 per volume. And that is compared to the WAG scenario. And in the WAG scenario, we started out with gas, followed it with water. So 1/10 of a per volume with the gas first, 1/10 of a per volume with the water, and then I'm changing back to gas. And after the second gas cycles, then I see these results. The difference here is due to the fact that we see a 3-phase zone near the injection well, and we see that gas is then distributed to the lower part of this vertical section. And this, but the frontal movement of these two channels that are formed, one on top and one in the middle, that is kind of sliding upwards, is recognized on both these cases, both for the WAG case and for the gas injection case, when we're using this max mobility type of REL pumps. Actually the REL pumps are given below here on the two last graphs here, showing that the gas injection relative permeability, and we see that we're getting much lower relative permeability near the injector due to that you are trapping a lot of gas. So the total mobility is low, and we see that we have a lower saturation on top of the reservoirs, but also in these fingers being formed. So in this case, what would happen to the end of the production? Well, if I go for the long-time production that I didn't show here, the WAG is doing much better than the gas injection. And the gas injection leaves behind large area which is unswept. But in the end, then with the WAG injection, we are getting very good displacement. So what's the the conclusion of this? Well, if you do short WAG cycles, we see also that the relative permeability input. I did this with max mobility approach. I could have done it with a gravity stable gas injection well pumped. I would get nearly the same. And the reason why is that fingers are suppressed by the slugging gas. Water is then stopping it up and trapping some gas, and the new gas cycle will not be able then to transport for a long time before it will, and we are changing back again to water. And thereby we have discontinuity in the gas phase and with the very short slugs. And we did the same thing with the larger slugs. And with the larger slugs of gas, then you immediately say similarity to the gas injection case. So you're converting it towards the gas injection case. So it's a beneficial from this point of view that to go with short slugs in WAG cycles, if possible. Another thing that came up is we are looking at the force balance here between viscous forces, capillary forces, gravity. And gravity, in this case, can work both ways for the gas. It could have a buoyancy that the gas is driving upwards, or you could have a kind of gravity stable injection if you inject it from the top and have a kind of angle on your reservoir. So, but what we see now that we need to consider the anisotropy of the relative permeability in order to progress further. So thereby what we are seeing is that we have perpendicular to the transport pathway, the relative permeability may be different, and we will test that out and see how it's important. I hope it's not important because it's going to create very much complexity if we need it. But it's important for in the near valuable region, then the gas moving forward in the direction of the pressure gradient in the reservoir, and then the buoyancy forces, which is then driving the gas upwards, will need to have two different relative permeability along the direction of flow and perpendicular to the direction of flow, and maybe two sets of rail pumps on the vertical movement of gas. Okay, now I'm into what's new in this chair compared to what we've been doing before. We are changing a bit, and one inspiration was this kind of paper in Journal of Petroleum Technology 1 year ago with Judy Feder, and saying that some companies push hard and fast to decarbonize energy and move into new and renewable resources. Other focus on cleaner, more efficient hydrocarbon, and which approach will win and get the upper hand. But I think that's the wrong question, but in my view, we have to do both. So there's no way around it. So we have to focus on cleaner, more efficient hydrocarbon production, and to decarbonize energy and move into economically new and renewable energy sources. Both direction has to go, at least for the next maybe 20, 30 years. So we should do it and clean up but how can we do it? Well, in this case, we have, we know that producing an oil barrel gives CO2 intensity of 222 kilos per barrel. Consume less fossil fuel is a goal, but it's not realistic yet for a long time. So then we have to look at CO2 capture, and that has to be developed over a long time also, because what's needed is to go from 1.5 to 5 billion tons of CO2 per year should be captured. And as an example, there's a small case in Norway on Sleipner field, which stores 1 million tons per year. So you need at least 1,000 times that to really make it count. So we're going to go in that direction, but as fast as possible. But it's not realistic to really make a big jump quick. And then we have the last point is that less CO2 production, kind of preventive methods during transition period, cleaner production of hydrocarbon, and how can we do it? So I'm going into that. So with these processes that you've seen, WAG process, for instance, on the polymer, we are going into, Dennis was talking about life cycle assessment. Here's another life cycle assessment. I'm looking at the energy involved in any of these processes. So if you go all the way from the source you have for injectant, the oil production, and then all the way to the refinery. You can look at the carbon footprint you made for the whole process. And we are looking at what's called the exergy, which is defined at the bottom there as the amount of work, entropy, minus free energy the system can perform when it's brought into thermodynamic equilibrium with its environment. So here we can put in the efficiency of the processing, energy we get out of the system by production, minus the energy we had to put in, and divided by the total amount of energy produced. So thereby we have one thing more that Dennis can put into his optimization. So he's not running out of work for a long time now. But it's quite important to look at these considerations for the field, and that includes everything, all the way from start of the production to the oil field, and then all the way to the refinery, as mentioned. It's just an example of, I mentioned that the polymer could be very efficient. This is a case from Ferrazade at Delft, and it's from this year. So it's looking at CO2 intensity. And if you look at the CO2 intensity, if you come up to water cut of 80%, you see it's shooting up like crazy. So thereby, one way to keep it low is to start at maybe at 70% water cut and say, okay, we should consider doing polymer in order to keep the CO2 footprint as low as possible. So we can clean up our act to some degree, and which I think is quite important. Of course, at the same time, we want this oil out as quick as possible, in the sense also that will be from an economical point of view, but also from this minimizing CO2 emission. Then we are looking at the way to design the process in order to get maximum effect of the process as fast as possible. Now we're not looking at the total production altogether, but we are looking at how fast can we accelerate the oil production and get it done with a much shorter time period. One other case is actually also for more energy efficient recovery processes, is in addition to fast oil production, less carbon footprint for that reason, but also to use less chemicals, less polymer. If you can get away with combining it like this low salinity polymer, we will see that we are then gaining a process which maybe are reducing the polymer is more efficient at low salinity, gives you higher viscosity, and you can go with lower concentration. So lower concentration means less carbon footprint on the production side of the chemicals. And that would be a benefit for that you are doing a more efficient process. We have to think along these lines also to look at different steps: injection pumps, artificial lift, water treatment, oil heating, oil transport, other things, and so on. What are the contribution, and how could we minimize the carbon footprint or CO2 emission for this process? Here's just for a polymer flood. At the start of the polymer flood, at 0.3 pore volume of polymer, and then at 1.3 towards the end. We're looking at first at energy invested, and then we see that the main part here is artificially lift in this case, and that diminishes over time. And other like polymer manufacturer comes into as a key element. But if you're looking at the CO2 emission, it more or less gives a very similar type of picture. And we can look at the energy invested compared to CO2 emission and find out the way where should we attack the process in order to minimize the carbon footprint for the whole process. What are the key elements, and what is not so important because the contribution is so small that we can ignore it. Here's a case from a field which was not able to give the name on, but we had production data from regions of water flood injection, and then which has the same maturity of the field production and polymer injection over a similar period. And we saw that the carbon footprint here, or CO2 intensity, is much lower for the polymer injection. You are already into a stage where we have a high water cut in this case, but it's not extreme, so it's like around 70%. So in conclusion, we need to focus on cleaner, more efficient hydrocarbons, and also to decarbonize energy and move into economical new and renewable energy sources. So go do both. Improve the utilization factor or efficiency of the injectant is a key element. Like for instance with the low salinity polymer, which requires less injectant, and thereby we get a more efficient process, reducing the CO2 intensity of carbon production and hydrocarbon production. Polymer flood at the late stage seems to be a good idea in many cases and can be an effective way of reducing carbon footprint. So one recommendation is to software companies, which have done a good job of developing reservoir simulators, but they should also include options of including the net energy consumption on the processes, and leave that as a simulation output. So I would like to see XRG and looking at the energy out minus energy in over the energy out, so it normalized energy efficiency, and then look at CO2 intensity of different processes, and where is your problem in the processes. You can identify that, and that could help you in the sense of cleaning up the act and making a better production for the coming years. Okay, by that I acknowledge energy simulation for coming in as for new chair period and also my sponsors on the JRP, and also good cooperation with Unicamp and Heriot-Watt, GTU Denmark and Delft, the Technical University in Delft. So thank you very much.
Thank you. So there are a couple of questions online. First one from Dr. Russell Johns, a former energy simulation research chair at Penn State University. He asked about WEC injects a significant amount of water that occupies pore space so that less CO2 is stored. Why not inject CO2 continuously at the top of the reservoir and produce fluids, oil and water at the bottom in a more gravity stable process? Thus more CO2 can be stored because of incompressible oil and gas, oil and water are being produced below. This would seem to be superior to production at the top and in terms of mass storage and probably even recovery.
It goes beyond a bit of what I've been talking about, but I agree with this statement. So CO2 injection then on the top and on the gravity stable displacement is always a good idea. But it's not always you can utilize this. It depends on the reservoir size.
The structure.
Yeah.
Yeah.
It's a structure.
Yeah, my answer would be also looking at the reservoir structure. You got to have a trap, otherwise CO2 would go miles and miles away from your reservoir. Yeah. So question from Hao Ming Ma. Regarding your CO2 intensity of 1 barrel of oil, roughly about 422 kilogram of CO2 equivalent per barrel. What is the life cycle system boundary?
What's the life cycle system
boundary? I don't know what that
would mean. I don't understand the relationship, but okay. The life cycle, what we are looking for is to minimize the carbon footprint on the processes, and what I've been talking about has been mostly on the EOR process. We have a carbon CO2 intensity of any barrel we are producing, but we don't have an option yet of stopping oil production completely. So thereby we have to produce it and accept that it will give you 422 kilos per barrel of oil being produced. But what you have is in some cases an inefficient process also. And the inefficiency of the process is the thing that I'm attacking, to make it more efficient in the sense of not waste energy, and to find different ways of minimizing the carbon footprint during the production. I think there's many other cases that we've been looking at, for instance, on energy, instead of using the hydrocarbon gas as a source for the production. We've seen in Oman coming up with using solar energy instead. There's a transition here to think through the process and make an effort on minimizing carbon footprint. And that's very much, I think, will be coming.
Okay. One other question online from our good associate at Chevron, actually a former associate at Chevron who supports our chair at University of Southern California, Dr. Kaveh Dagani. His question is, are you planning to study the impact of different injection schemes to incorporate CO2 injection, CO2/WEC, or CO2/WEC/polymer on the recovery, as well as CO2 sequestration or storage aspect in the reservoir? The optimization of EOR benefit versus CO2 storage can be very helpful.
That was very many questions into one. I think I will write him an email back.
Okay, you know him, so.
Yeah.
But certainly it's a good idea to optimize, in terms of how much economically, in terms of UR, and then how much physically you can store both concurrently or down the road.
Yeah.
Okay. So yeah, send me an email. Thank you. Any further questions? If not, let's pull up an online